So for this section and almost every other lengthier section, I'm going to break this into two parts. I probably should have did that with section 1.1 because that was pretty long. But it just makes it a little bit easier for you to go through, and it definitely makes it easier for me when recording as well. I could kind of do it in smaller chunks. So this focus in this section is going to be on transformation of functions, taking a parent graph or what we call an old function and coming up with a new function. So first we're just going to take a look at horizontal and vertical shifts. So this value of C is going to be a constant. So for the first four facts here, we're going to suppose that C is greater than 0. And when we look at a function f of x where we see plus some value C, this will shift the graph of y equals f of x up C units. And then just the opposite, when we see y equals f of x minus C, this will shift the graph of f of x down C units. So when we look here, I'm just going to kind of pick an x cubed as our function. So here's x cubed, and then if I see x cubed plus 3, definitely want to bring that back down. We see that, and the origins sometimes, or a vertex if we have one, is a good way to kind of view the transformation here. So if we're looking at where this kind of goes across to turn up at 0, 0, next it's at 0, 3, and then if we see x cubed minus 1, we'll see a shift of 1 unit down, as we see right here. So nothing physically has changed in the direction or the shape of the graph. It has just been shifted up 3 units or down 1 unit. All right, next, if we look at the third fact, if we see y is equal to f and in parentheses we see an x minus c, this is now a horizontal shift, and it actually shifts it in the opposite direction. So in this case, when we see a minus c, it's going to shift it c units to the right. And then when we see a plus c, x plus c in parentheses, this will shift the graph of f of x to the left c units. So again, if we take a look at x cubed, y equals x cubed, I'll just graph that parent function. And then if I see in parentheses here, let's do x minus 4. This will shift 4 units to the right. I have to cube that. Now it's shifted 4 units to the right. And then if I see maybe an x minus 3, that cubed. Sorry, let's do x plus 3. That's shifted 3 units to the left. All right, on the next page, there's going to be some facts about stretching and shrinking. So in this case, we're going to suppose that C is greater than 1, and then the following facts will take effect. So please make sure you pause this video at any time. You need to maybe write down some questions to ask me in class when you see me, or just to take your time to copy this down. One thing you'll find out about me is I give way more examples than are probably necessary, but I think that they ultimately help at the end. So here, if we see a constant getting multiplied by our function, this will stretch the graph of f of x vertically by a factor of c. And if we see the reciprocal, since c is greater than 1, 1 over c just becomes the reciprocal. That being multiplied by f of x will shrink the graph of f of x vertically by a factor of c. So let's take a quick look at our x cubed. Again, there's our parent graph. So now let's see if I type in a 2x cubed. It has stretched it vertically, meaning our y values are getting larger a lot quicker, so it looks like the graph is actually skinnier. And that's what happens. Think of like a like silly putty or whatever you could stretch vertically. It is going to get skinnier going across, or the width of it will get skinnier. And then if we take a fraction, let's say it's going to be 1/2 times x cubed. This actually got a little bit wider because it was shrinking it vertically. So if you press down on something vertically, it actually gets a little bit wider. So stretching it vertically, it's less wide, it's a little bit skinnier. Shrinking it vertically or compressing it gets a little bit wider. And sometimes that can be confusing with horizontal, but we'll just take a look at this, and we can always substitute values in to help us as well. So our next two facts is when we see c on the inside of the parentheses as c itself and then as a fraction. So if y is equal to f of c times x, this will shrink the graph of f of x horizontally by a factor of c. And then if y is equal to f of the reciprocal of c times x, this will stretch the graph horizontally by a factor of c. So let's take a look at those. Again, I'm just going to graph x cubed. So now inside parentheses, if I see a 2x and then I cube that. All right, so horizontally, it got shorter. So this was a shrink horizontally. We're not looking at this vertically because of where that 2 was. It was inside the parentheses. So this is a shrink horizontally, or it got compressed horizontally, which makes it longer, less wide and longer. So essentially the same effect as the vertical stretch. And then if we looked at 1/2 and then x and then we cube that, it should become wider. We should be stretching it horizontally. So it's definitely wider horizontally. Then our next two facts are just with reflections. So for 5, if we see y is equal to the opposite of f of x, this takes the opposite of the y values because that's what f of x is. This will reflect the graph of f of x about the x-axis. If we see the negative on the inside of the parentheses, y is equal to f of the opposite of x, this will reflect the graph of f of x about the y-axis. And let's take a look at that. Now I'm actually going to switch the function here a little bit. So let's just take a look at, I'll just do a line. Let's see how that looks. So let's say I do 3x. I'll just do y equals 3x. So now if I did a negative 3x, we could see that that reflects over the y-axis here. But notice it also reflects over the x-axis, or it reflects first over the x-axis, so it's showing you that it's the opposite. But then, just based on the nature of it, and this would have happened with x cubed as well, if I just did 3 times a negative x, because that turns out to be negative 3x again, it's going to give us the same. So here we just happen to have that symmetry, or it's just reflecting over the x-axis for the same function as well. And a lot of times we have that. If we get more into more complicated graphs, which I want to say for examples, we'll see that with those examples. All right, so this is what I want you to practice. If you can pause the video, graph 2 coordinate planes. We're going to start with y equals x squared, and then we're going to go through a series of transformations. So go ahead and pause the video. All right, we're going to graph the parent function with each one. So again, pause the video and see if you could do y equals x squared minus 4, and y equals x minus 3, that quantity squared, all by yourself, by hand, before you continue playing the video. All right, so looking at how to graph y equals x squared, again, it's a parabola, very basic. It's the parent function, so the vertex is going to be at 0, 0. Here, the value of a is 1. So if we count over 1, we count up 1 on either side of the vertex. Over 2, 2 squared is 4, so we count up 4. And over 3, up 9, because 3 squared is 9. And then we get our parent function. All right, next, I'm only going to graph the blue and the purple functions over here as well, and then on the next graph, I'll do the other two. So x squared minus 4 just means we have a vertical shift of down 4 units. So now my new vertex starts here. And again, I count over and up the same way. Over 1, up 1, over 2, up 4, and over 3, up 9. So the size of the parabola did not change. We did not stretch it or shrink the graph. We're just looking at a vertical shift of 4 units down. And then the purple one, we actually get a horizontal shift of 3 units to the right. And again, it's just a new vertex, so we just go over 1, up 1. We still count the same way, over 2, up 4, and over 3, up 9. Now you can check on Desmos or any kind of graphing calculator if you want anything you do by hand. you could still check that way. All right, for the next two, again, I'm just going to start by graphing the parent function again. So we start here at the origin and count over 1 up 1, over 2 up 4, and over 3 up 9. All right, so if the stretching and shrinking transformations are a little bit complicated, we could just start by picking some values and kind of going with the table method. I always find that to be a little bit easier. So if x is 0, I'm looking at y equals 2x squared. If x is 0, 0 squared is 0 times 2, so I still have the same origin. Now here in this case, a is 1. So, I'm sorry, a is 2. So that's going to change what I count up, and that's essentially what's giving me that shift. So a is 2. So if I go over 1, 1 squared is 1, and then I double that, I'm actually just going up 2. So over 1, up 2 on either side. If I count over 2, x is 2, so 2 squared is 4. If I double that, I'm going up 8. So I double what I normally go up by squaring after I square them. Now, unfortunately, that's all I could fit on mine. So we're looking at a vertical stretch, which means our parabola looks skinnier. And then for this last one, here a is a -1. It's that leading coefficient. So this is just going to be a reflection over the x-axis. So again, if x is 0, it's 0. If x is 1, I'm going to get 1 squared is 1, and then the opposite will be a -1. So that's what causes the parabola to open down when the leading coefficient is negative. If I still count over 2, I'm counting down 4 this time. And if I count over 3, I'm counting down 9. So there's practice using y equals x squared as our parent graph. The next set will practice with using y equals the square root of x. So again, pause the video, make 2 new coordinate planes, and see if you can remember how to graph the parent function y equals the square root of x. Now, the square root of x looks like the top half of a sideways parabola. So again, if we chose 0 for x, square root of 0 is 0. Square root of 1 is 1. So if I go over 1, I go up the square root. So sort of just the opposite operation of what we were just doing. If I go over 2, square root of 2 is not a nice integer value. Square root of 3 isn't, but square root of 4. So if I count over 4, I'm going up 2. Next, I want to jump to 9. Square root of 9 is 3. Now, these are all positives, so I only see the upper half of a sideways parabola. So this is our parent function, y equals the square root of x. Again, pause the video, try graphing the transformations here. Y equals the square root of x plus 3, and y equals the square root of the quantity x plus 4. All right, so y equals the square root of x plus 3 is going to be a vertical shift up 3 units. So we just start here. Again, we count over 1 up 1, over 4 up 2, and then over 9 up 3. And then looking at the third one here, y is equal to the square root of the quantity x plus 4. That's going to be a horizontal shift 4 units to the left. So now my new starting point is right here. And again, over 1 up 1, over 4 up 2, and over 9 up 3. All right, before we graph the last two, again, you could pause the video if you didn't already start a new coordinate plane. We're just going to go ahead and graph the parent function again. Now think about this. Here we have a fraction that's on the inside, so the x values are getting smaller because we're taking half of them, then we're still going to take the square root of that. So the x values are getting smaller. So if we go ahead, we don't even have to worry about what we would describe it as. All we have to do is pick some x values. So again, if we start at 0, x is 0, half of 0 is 0, square root of 0 is 0. So we have this same starting point. If we go over 1, half of 1 is a half. Square root of a half is a number we really don't want to work with, so let's skip it. If we go over to 2, half of 2 is 1, and square root of 1 is 1. If we go over to 3, half of 3 is not a nice number. Half of 4 isn't a nice perfect square. How about we go over 8, because half of 8 is 4, and the square root of 4 is 2. So we see that we get a slight change here. So when we see that 1/2 inside, it's actually going to be a horizontal stretch, or it actually looks longer horizontally than the original of the parent graph. And for the last one here, we have y is equal to the square root of the opposite of x. Well, this is going to, if you go back to our list, when we see the negative contained within the function or in the parentheses, we get a reflection over the y-axis. And this is why, because if I chose x to be a 1, -1 is underneath the radical, and I have a problem with that. I can't take the square root of -1. So the original x values I pick have to be negative. So if I chose a -1, square root of the opposite of -1 now becomes square root of +1. So this is what I'm getting as the result here. Or 0, that won't change. But now if I go over to -4, the opposite of -4 is +4, square root of that is 2, and then I'll go to -9. The opposite of -9 is 9, square root of that is a +3. So this is what gives me that reflection over the y-axis and not the x-axis. All right, we'll just do one more problem from, actually I'll change it. We'll go a little bit further, still for part 1. All right, so pause the video again, copy this down. How is the graph of f of x equal to x squared minus 4x plus 5 shifted from the graph of f of x is equal to x squared? So see if you could come up with that first before I go over this. So there's two ways to determine the way we shift or the vertex here, because we could always compare the vertex of the new function compared to the old function. One way is by completing the square to write our quadratic in vertex form. So we complete the square. And then I'll show you guys another way, just memorizing two little formulas to do this. So I'm going to start with y. Instead of f of x, I'll call it y is equal to x squared minus 4x plus 5. Now with these first two terms, I want to add another term to it to make it a perfect square trinomial. So I'm going to do that. I'm going to group it in its own quantity here, leave a little bit of space, and then I'll have the 5 plus 5. Now in some situations we can move the 5 to the other side, but then we end up moving it back at the end, so we can avoid that. To complete the square, I take half of the linear coefficient, which is 2, and then I square it. So I'm going to add a 4. Now because I could do this right away because the leading coefficient was 1. If it were something else, I'd have to factor it out. What I really added to this was a 4, but I have to keep it balanced, so I need to subtract a 4 over here. So now I want to factor this perfect square trinomial into the quantity x minus 2, and then I'll get a plus 1 here. So this tells me from f of x is equal to x squared, I have a shift of 2 units to the right and 1 unit up. Or the vertex is at positive 2, 1. We take the opposite of the inside number and then the same as the outside number. So my vertex is at 2, 1. Here's a different way to do this. The vertex is made up of two special values here. The special x value is actually called h, and the special y value is called k. So you find h by taking the opposite of b over 2a, and k is equal to f of h. So to figure this out, if we look at a quadratic function in standard form or general form is what they call it, it's y is equal to ax squared plus bx plus c. So in this case, b is -4. So h is equal to the opposite of -4 over 2 times a is 1. So I get 4 over 2, which is 2. So k is equal to f of 2. So this will give me, I'm looking right up here, 2 squared is 4. Minus 4 times 2 is 8, and then plus 5. So k is going to equal 4 minus 8 is -4 plus 5 is 1. So I get a vertex here of 2, 1, which matches, or I could substitute it back into the vertex form. Vertex form is just y equals a times x minus h squared plus k. So again, the vertex comes from hk. So plugging this in, if I had to work backwards, I would say y is equal, again, a is 1. Then I would have x minus h, which is 2, x minus 2 squared, plus my k value, which is plus 1. So this still takes us back to, this is our answer here. We are shifting 2 units to the right and 1 unit up from the original graph. All right, next we're going to take a look at what we consider a combination of functions. And this will kind of wrap up the part 1, and then the continuation of this section will go on in part 2, which I'll post separately. All right, so a combination of functions, or we could even get into composition of functions. We might see things written out like f plus g and then see the x, but this just means f of x plus g of x. That's the simplest one to do. When we see subtraction, though, we have to be careful because a lot of times our functions are polynomials. So if we have to subtract more than one term, we need to distribute that minus sign. So this becomes f of x, and then I want to keep in brackets here g of x, just so we remember to change the signs. This means f times g of x, so f of x times g of x. And a lot of times, if they're binomials, trinomials, we have to use the distributive property. Next is just division. So when we see it written as f over g of x, just becomes f of x over g of x. Again, keep in mind g of x should not equal 0. But this last one here, this is the composition of functions. So this, written out this way, becomes f of g of x. So this is a composition of functions. And let's take a look at some examples here. Now, a lot of times with these lessons that I'm going to make as videos, they may not take as long to view as sitting in class, but that's because I'm letting you guys, or having you guys, work in class a lot on your own, which fills up the time. So it's going to benefit you the best to not only, like I said, come to class, but to still view these lessons, whether you're sitting in class for this lesson or not, especially if you're not, you want to view this lesson. So a lot of times I just like to give plenty of examples, maybe even more than what you need or think you need, but it's always good to look these over. As I said, what I give in class are going to be very similar problems, but definitely different to provide you with more practice as well. All right, so here we're looking at A. We have f of x is equal to x minus 7, g of x is x squared plus 6x. So the first, I'm just asking you to add these two together. Again, please feel free to pause the video and try A and B on your own, and then resume playing. So if we're just adding these together, just f of x plus g of x, this just becomes x minus 7. Since I'm adding, I don't need to worry about changing signs, so then I get plus x squared plus 6x. Now all I can do is combine like terms, so I just get x squared, x plus 6x will give me 7x minus 7. So nothing to really watch out for there. But for b, I have f of x minus the quantity of g of x, and that's going to matter here. So we have x minus 7 minus the x squared plus 6x. So by subtracting both of these, I'll get x minus 7 minus x squared minus a 6x. Now, if there happened to be a minus sign in here, it would definitely change it to a positive. I'll continue this over here. Here, I always like to put the terms with the largest exponent first. Just looks proper. We'll have a negative x squared. X minus 6x will give me a minus 5x, and then a minus 7. And on another note, I'd like to point out, if I do happen to make a mistake in here, please let me know so I can go back and fix that. I do always try to double check my work, but sometimes a little mistake is very easy to overlook. But please let me know if you do see any errors or just have questions in general over the problems as well. All right, next we're looking at f of x times g of x. So here we're getting the quantity x minus 7 times the quantity x squared plus 6x, and we just distribute carefully. X times x squared is x cubed. X times 6x will give me plus 6x squared. Negative 7 times x squared is minus 7x squared. And then negative 7 times 6x is minus 42x. So combining our like terms here, we just get an x cubed minus an x squared minus 42x. Next one, we have division, so we're just taking f of x over g of x, and this becomes x minus 7 over x squared plus 6x. What we would try to do in this case is see if we could factor anything out and divide out common factors. In this case, there's nothing we can do, so that is how we leave it. All right, so again, I'm just going to recopy this off to the side. F of x is x minus 7. G of x is x squared plus 6x. So when I look at f of g of x, this just becomes f of g of x is x squared plus 6x. So just as we practiced in one example in section 1.1, I just want to take this x squared plus 6x and just drop it in up here where I see the x. So this just becomes x squared plus 6x minus 7. So this whole these first two terms, that's just what I'm replacing or putting in for the x. Now there's nothing else I can do or combine, so that's how I'm leaving it. Okay, next, this notation is just the reverse. It's saying g of f of x, or g of x minus 7. So again, with g of x being x squared plus 6x, wherever I see an x, I'm replacing it with an x minus 7. So this becomes x minus 7, that quantity squared, plus 6 times x minus 7. And then we'll expand this. Let me move this one out of the way. All right, so this becomes x minus 7 times x minus 7. We can distribute the 6 here, 6x minus 42. And at some point, keep practicing these. We want to be able to just really get to the expression simply by looking at this, and that's what I'm going to do. X times x is x squared. Outside and inside both give me a minus 7x, so I'll get a minus 14x and then plus a 49. And then plus 6x minus 42. Combining my like terms, I'll get an x squared. Negative 14x plus 6x will give me a minus 8x. 49 minus 42 will give me a 7. And then another way we could look at this, yes, it is possible to compose one function into itself again. So this just becomes g of x squared plus 6x, which means we're substituting in an x squared plus 6x inside the g of x. So this becomes x squared plus 6x squared plus 6 times x squared plus 6x. So again, since g of x is equal to x squared plus 6x, wherever I see the x, I'm putting in the x squared plus 6x again, and over here, x squared plus 6x again. So again, we have to expand this. We have this quantity squared. You may not need to write it out, but as far as my notes, I'm going to do that for you. So here, very carefully, we'll get an x to the 4th. On the outside and inside, I'll get a 6x cubed. So if I have two of those, I'll have a 12x cubed. And then last, we'll get a 36x squared. Over here, if I distribute, we'll get a 6x squared plus 36x. And combining like terms, we have an x to the 4th. We'll get, that should have been a 12x cubed. So we'll still have the 12x cubed. Here we'll get a 42x squared plus a 36x. All right, let's try one more example like this, and that'll wrap up part 1. All right, so here I'm giving you two functions, f of x and g of x. Go ahead and figure this out. I'll just give you a hint. Here, this f of g means f of g of x. Now we're going to go in reverse, g of f of x. And then also state their domain. So go ahead and pause the video, give this a try, and then check your work. So f of g of x now becomes f of 3x over x minus 2. Now f of x is just whatever we're giving it squared plus 2. So we're giving this 3x over x minus 2 squared plus 2. Now, because I want to state the domain, I have a fraction here. I like to see denominators stay in factored form. It just makes it easier to state the domain. So I'm just going to go ahead and square the 3x, which will give me a 9x squared. Then the denominator, I'm just going to leave as x minus 2 squared. Then I'll put the plus 2. So that's what f of g of x is equal to. Now, looking at the denominator, I can't let that be 0. What's going to let it or cause it to be 0 when x is 2? So we can't let x equal to. So our domain, you can write out, and I'm fine with this, it's just on WebAssign, I think they ask primarily for interval notation. So you could say all real numbers except x equals 2, or you could use interval notation, and to write that this way, it would just be negative infinity to 2. We're not including the 2. We use a union symbol, and then 2 to infinity would be the domain. Next, we have g of f of x, which becomes g of x squared plus 2. So here I have a fraction, so up top is going to be 3 times the quantity x squared plus 2. Then in our denominator, it becomes x squared plus 2 minus 2. Simplifying this, up top I'll have 3x squared plus 6 just over x squared. Nothing else to do. The x squares do not cross out. We have a binomial on the top and a monomial in the denominator. So here, everything's good except my denominator can't be 0, and that's only going to happen when x is 0. So x could be any number but 0. So my domain is negative infinity to 0, and then we'll join that with 0 to infinity. All right, so that's everything for section 1.3 part 1. Part 2, we're going to pick back up with some more graphs looking at x and y intercepts. We'll also practice just some review problems, some problems that you saw also as examples in section 1.1. So as always, guys, I'm going to say this at the end of any lesson. Let me know if you have any questions.